Hello Year 12 Math Methods students. Welcome back to another video on normal distributions. This time we're up to 16C, and this is where we start to look at using the calculator to determine probabilities associated with normal distributions. You'll hopefully remember from the previous section that we looked at some approximations using the 68, 95, 99.7% rule. This section is where we get a little bit more precise, and we actually use our calculator to determine exact proportions or probabilities, I suppose, depending on the way the question's framed. And it is important to know that in nearly all circumstances, this is the way that we calculate normal probabilities. So we don't typically use those approximations unless it's very clear in the question that we're using those approximate percentages. So a couple of little reminders. The first one is that the standard normal distribution, whenever we refer to the standard normal distribution, that's the normal distribution that has a mean of 0 and a variance of 1, which also means the standard deviation is 1. Standard normal distribution is often represented with Z as its variable, or it can be written this way as well, to say that Z is a normally distributed variable with a mean of 0, variance of 1. And we also know that we can take other normal distributions and transform them to the standard normal distribution using this formula. So in other words, when you have, we looked at the previous example with IQ scores where the mean is 100 and the standard deviation is 15, you can convert numbers from that distribution back into a standard score or a standard value using this formula here. So that was just a bit of a recap of what we've gone through so far. When we come to calculate exact probabilities associated with normal distributions, the function that you're looking for is called norm CDF, and we get there using interactive distribution continuous norm CDF. So this is a good thing to highlight and have in your summary book. But as you get to practice it more and more throughout the topic, you're going to kind of remember where that is anyway. All right, let's have a look at a couple of examples of putting this into place. So for example 1 here, it says, if the variable Z has standard normal distribution, calculate the following probabilities correct to 2 decimal places. So the first one is the probability that Z is greater than 1.5. So that essentially means, to interpret that, what's the probability that a particular score would be more than 1.5 standard deviations above the mean? Okay, so it's not essential to sketch your bell curve for these ones, but if you were to sketch it, very roughly speaking, remember with the standard normal distribution, the mean is 0, so 1, 2, and 3. We'd be kind of talking about what's the probability that we're above this value here, because each standard deviation in this situation is 1. One of the reasons that it's sometimes good to do this bell curve sketch, even if you don't need it, is because it gives you a sense of what the probability looks like it should be. Roughly speaking, we're expecting a relatively small probability because much more than half of the distribution is on the left-hand side of that line that I've drawn. So there's only a very small percentage of the distribution that's above 1.5. So let's run through the calculator commands. You're going to get very used to using these. So it's interactive, distribution, continuous. Remember, with normal distributions, we're always thinking about variables that are continuous now. So time, distance, that sort of thing. So that's why it's under continuous and not discrete. And it's norm CDF. From here, you're prompted to put in the lower and the upper value. Now we just want 1.5 and above, or above 1.5. So we put in 1.5 as our lower, and our upper is essentially infinity. We just want anything above 1.5. And you actually do put in, under Math 2, the infinity symbol. The default setting for the standard deviation and the mean are 1 and 0. So if if it's a standard normal distribution like it is for this example, we actually just leave those two values. We hit OK, and we get our probability of 0.066 or 0.07 when we round that to 2 decimal places. Okay, so this probability was equal to 0.07. Like I said, picture not required for your working out, but just good to get some sense of what the probability is likely to be, and then you can evaluate, does that answer look like it makes sense or not? And certainly we were expecting a small probability, much less than a half, so that answer does seem realistic. Okay, part B. Like with any of these videos, you're more than welcome to pause the video now and have a go at the question first and then check your answer. But for this one, we're looking at the probability that Z would be less than 0.7. Again, if we were to sketch our bell curve with 0 in the middle, so 0.7, well, if here's one standard deviation above, 0.7 would be approximately here. So if we're looking at less than that score, we're now expecting a probability that's a bit over half, okay, because we should have more than half of the distribution below this value. And again, we go to our calculator to confirm that and get the exact probability. Once you've typed one of these in, you can just change these two numbers, but I might just run through so that you can remember: interactive, distribution, continuous, norm CDF. This time we want from 0.7 below, so our lower limit is actually negative infinity. Our upper is 0.7. Again, the standard deviation is 1, the mean is 0, so we're leaving those two values. And we get 0.758 or 0.76 as our probability. Okay, Thankfully as well, the norm CDF function that we've just been using on the calculator can also be used to determine probabilities for any normal distribution. So where you have a different mean and a different standard deviation besides 0 and 1. And so again, rather than using those approximate percentages for lots and lots of questions, you would have, you'd be using norm CDF to calculate probabilities. So here's a situation where we've got a normally distributed variable with a mean of 40 and a standard deviation of 5. All right, so those are the two key values we need to identify from the question. And then we've got to calculate some associated probabilities. So the first question here is asking us to find the probability that x is greater than or equal to 30 but less than or equal to 43. Again, I'm going to sketch the curve even though it's not 100% necessary, just good for your understanding. So here's the mean of 40. Standard deviation was 5, so if we mark our sort of 3 above, 3 below, we've got 45, 50, 35, 30. This is just good for our sort of visualizing the question. We're looking for between 30 and 45. Right, now it's a little bit harder to eyeball these when they're sort of between two values, but just to look at it, closely, maybe it's going to be a bit over half. It looks like a pretty decent chunk of the distribution here, so we're certainly not expecting a really small probability. To me, that looks like it's going to be a bit more than half the distribution, but of course we're going to get it on the calculator anyway, just to be sure. So interactive distribution, continuous, norm CDF. This time the lower value was 30, upper is 43. And here we've got to adjust the mean and the standard deviation. Now, in questions, often the mean will be written first and then the standard deviation, but in this screen, it's actually the standard deviation first. So be careful with that one. The standard deviation for this question was 5 and the mean was 40. Okay, and we get 0.70299. This said 3 decimal places, so that one would round to 0.703 because it was 0.7029. Okay, second part of the question gives us a conditional probability statement. And even though this is a normal distribution kind of question, you can still get conditional probability basically within any other type of probability question. Best thing to do with conditional probability is rewrite it using the formula. Remember that if it's the probability that x is greater than or equal to 30, given that x is less than or equal to 43, well, that just means it's the probability of both of those things happening. So greater than or equal to 30 and less than or equal to 43 over the probability of the condition that has occurred. So the probability of the second thing, if you like. In other words, probability that x is less than or equal to 43 is going to be on the bottom. Okay, so let's try to interpret this top statement. We're saying the probability that x is greater than or equal to 30 and less than or equal to 43. That's really saying that x has to be between 30 and 43. So the probability that's on top is essentially 30 is less than or equal to x, which is less than or equal to 43, over just the probability that x is less than or equal to 43. All right, so it's like saying, what's the probability that we're between 30 and 43 if we know that we're less than 43? So that's equal to the 0.703 that we worked out previously, because see how this numerator is the exact same answer that we got from part A. So it's the 0.70, I'm going to just put ... because I'm going to use the full number from the calculator, divided by, now, we haven't already got the probability that x is less than or equal to 43, so let's work that out. Interactive distribution, continuous, norm CDF. So if we want just less than 43, or less than or equal to 43, we're going to use negative infinity as our lower limit. Our upper limit is 43. Standard deviation is 5. The mean was 40. Okay, so we get 0.7257. 0.725, and again going to do the ... dots. And so really, our final answer is going to be the 0.7029, etc., over the 0.7257, etc., to get 0.9686, which would be 0.969 if we go to 3 decimal places. So 0.969. So often in those conditional probability questions with a normal distribution, you're actually going to have a norm CDF calculation to give you the numerator, then another norm CDF calculation to give you the denominator, and that will tell you your final probability. Alrighty. Pushing on, the last little thing we're going to look at here is, again, a calculator function called the inverse normal distribution. And basically this is used when we know the probability and we actually need to work backwards to find the associated x value. So in other words, it's kind of like a backwards question where we're saying, okay, if you have some probability that you you know already the value of the probability, and you want to find what number we would need to be less than or greater than to give us that probability, well, then we're really going to be using the inverse normal distribution because we're kind of working backwards. So there's a couple of ways you can do this on the calculator. There is a way to do it from the statistics screen, although I tend to think that this way is a little bit probably unnecessary. There is a slight advantage in one specific case, but I think for the most part, it's better to use the main screen. And so from the main screen, the best way to get to the inverse normal distribution is interactive distribution inverse, and then inverse norm CDF. Okay, as always, sometimes it's just best to see a couple of examples of these, but one of the key things that it is important to know is that this tail setting is really dictated to, or when we're going to use this is really depending on whether the question is giving you a less than or greater than value, or even between two values. Okay, and that's what will indicate whether we use left or right or center on our tail setting. Anyway, let's look at a couple of examples, and hopefully that function is going to start to make some sense. This is definitely a case where I'd be suggesting to sketch some bell curves, even though it's not necessary. It's a really good thing to make sure you're understanding and interpreting the question properly. All right, so if y is a normal random variable with a mean of 75 and a standard deviation of 6, so mean equals 75, standard deviation equals 6, calculate correct to two decimal places k such that the probability that y is less than or equal to k is 0.25. All right, so what this is saying is that we have a normal distribution, the mean is 75, and there's some value k, right, where the probability that we would get a result less than this k value is 0.25. Now that tells me a couple of things. It tells me that k must be less than the mean, because if you watch this sort of little bell curve sketch here, what we're saying is that there's really only 25% of the distribution below this value k. So straight away, I know that k needs to be a number that's less than 75, because if it was bigger than 75, it would have more than 50% of the distribution. So k must be less than 75. Now to work out the exact value of k, or the accurate value of k, we're going to use inverse norm CDF. So remember that was interactive distribution, inverse this time, and then inverse norm CDF. Now, this is another reason that the picture is important, because from the picture, we know that our tail setting needs to be left, because we're talking about a proportion that is to the left of a particular value. So we're using this tail setting left. The probability is 0.25, because that's the probability that was given to us. We also need to put in the standard deviation, which was 6, and the mean, which was 75. We hit OK, and we get 70.95. Right, now remember, we were expecting a value that's below the mean, so this seems like a realistic answer. And so using inverse norm, we've been able to determine that k is equal to 70 point, that was two decimal places, so 0.953 would be 70.95. Okay. Part B, similar question, but this is just saying there's some value a such that the probability that y is greater than or equal to a is equal to 0.6. Again, well, that's a pretty terrible normal distribution, but even a bad sketch is better than none. So if our mean is 75, and we're saying there's some value a where the probability that we're greater than or equal to a is equal to 0.6. Well, another way of saying that is saying if here's my value a, don't give myself much room to write. If there's a along this x-axis, the probability that we're greater than a is 60%. In other words, 60% of the distribution needs to be above this value a, which tells me that a must be less than the mean, okay? Because I need to have more than 50% of the distribution above a. Remember, the mean always cuts these normal distributions in half. So again, the sketch helps us to, one, estimate what our answer might be, but two, tell us that we're using this time a tail setting to the right, because we're looking at a percentage that is to the right of our particular value here. So when we go to use inverse norm CDF again, it's going to be interactive distribution inverse norm CDF, tail setting to the right, probability was 0.6, standard deviation was, I keep forgetting, 6, and the mean was 75. And so this time we're getting a value of 73.479, so 73.48. So A equals 73.48. Okay, so sketching those bell curves definitely makes these questions easier and really cuts down on your chances of making a mistake, which at the end of the day is what we're trying to avoid. So hopefully that's giving you a good sense of using the inverse normal distribution as well as the normal distribution. So remember that really what we've covered in this section is how you use your calculator to get these exact probabilities and these precise values rather than using those approximate percentages. As always, if you want some help with anything, please contact your teachers, but otherwise good luck with 16C and we'll see you in the next video.